You may have heard of the phrase, a large language model is nothing but a next word prediction machine. And while that may be true, it's also like saying a jet engine is nothing but a machine that pumps a lot of air. Welcome to our next series in AI and cybersecurity. So far, we've looked at hacking the layer of software that runs on top of large language models, Agentic AI, RAG chatbots, MCP servers. In this series, we will now look at hacking the large language model itself. Before we get to that, it's important we understand what a large language model is. We're not going to get into all the linear algebra and differential calculus involved, but we're going to understand the key concepts from a security researcher's perspective. So let's dive in. The first thing to understand is the word model in LLM. A model is nothing but a math function that maps to most of the data that we have at hand. So imagine we have data that has two columns. The first column, let's call it X, is the size of houses in a particular area. Corresponding to each X is a Y, which is the price that house got when it last sold. And if I am able to plot all of this data and get a function that maps every X to the Y, when I get a new X, a new house comes into the market, I should be able to map it to this formula and say, hey, based on what we've seen, this is the price that this house should command in the market. Now, there would be a lot of other parameters, the location of the house, the number of bathrooms, so on and so forth. But for our purpose, we're going to look at only these two parameters. So let's say I have two house values and I plot them on a graph. Now I want to find a line that maps to these two values. That's pretty simple, right? And so I get something of the form y equal to mx plus b, which from elementary school maths, I know that the value y is equal to the slope m multiplied by x plus a value b, which is where on the y-axis the line starts. In this case, starts at 0. So the bias would be 0. Let's say I add more data points to my model. Now the line changes, you can see. And if I keep doing that, the values m and b will keep changing for the line to be aligned to as much of the data as possible. And that's pretty much it. But not all situations and all problems will fit into this very simple linear regression model. Sometimes I have data that falls more into clusters. So I could have data that looks a lot more like this. And in this case, I could use a model called a support vector machine, which is a very simple but highly effective model that learns the boundaries when fed a data set. And when a new data point comes in, it plots based on these boundaries where the data would lie and therefore predicts the outcome of it. Now, these are very simple models and training them is not very compute intensive, but they don't solve a lot of the key problems that we face, such as interpreting images and video and human language. So how do models actually learn the right parameters for the mathematical function that we're using? One of the very popular algorithms we use is called gradient descent. This algorithm uses differential calculus to look at the value that came out from this model with the current set of parameters versus what the actual value is from the real world. So the price predicted by the model versus the actual price that I have from my data set. Looks at the difference and then tries to find the next value of the parameters that would bring me one step closer to the expected output. And by repeating this process over and over again, by finding a local minima, I keep doing this and I reach a stage where the predicted values now match very closely. The loss between the actual value and the predicted value is so less that I can say the model actually mirrors my data set. And that's when we say the model has been trained. So how do we actually find the right parameters for our model? Let's watch the learning process take place. We start with random values and we measure the distance from the actual value that is there in our data set versus the value that the model is predicting. And this gives me the error. We square these errors. That eliminates negative errors. And then we sum this up. We square these errors so that negative errors don't cross out the positive errors. And then we sum up these errors. And based on that, we get a single loss value for that data point. Now, here's where it gets pretty beautiful. Imagine every value M and B in the universe of values, resulting in a specific loss value. At some stage, this loss value will keep coming down, create a valley, and I use a differential calculus formula called gradient descent to find what the next value should be to get me closer to the descent. It's like a hiker trying to figure out the shortest way back to base camp. And this should also tell us a little bit about how do we hack stuff. If the data is poisoned, or if the training algorithm is poisoned, the model will learn the wrong weights. These simple ideas are effective for a lot of problem statements out there, but not for more complex use cases like learning text and video and even generating content. And here's where comes the concept of neural networks. A neuron takes inputs, let's call them x1, x2, x3, multiplied by weights w1, w2, w3, summed up, and each neuron carries a bias parameter which is added to these sums. And this entire sum is now put through what's called an activation function. A popular choice of activation functions is ReLU or sigmoid, tanh, leaky ReLU. Essentially what the ReLU does is if it's a negative value, the output is 0. If it's a positive value, the output carries on as it is. You can see that in this simple network, I have 3 nodes in the input layer. I have 2 layers in the middle called hidden layers, each of which has 4 nodes, and I have 1 output layer. Even with a simple model like this, we are looking at 41 parameters, the weights and the biases. And as I pass data through it, I keep getting output, and I keep changing these parameters, the weights between these 2 nodes and the bias value, and I keep generating a different output with changes. Even the smallest neural networks would have 10,000 parameters. GPT-3 has 175 billion parameters. GPT-4 is said to have 1.8 trillion parameters. Now, how do we train these models? The same concept we looked at earlier. Run a forward pass, calculate the loss function. I needed a value of 0.8 as per my data set. I got 0.49. Send this information back, but in a way where I understand which node, changing which bias value and which weight value will have the most impact in getting me as close as possible to the expected output. So I compute the loss, send the data back, update the weights. Repeat this multiple times, and I keep moving closer, as you can see, to my expected target value. Now we're getting closer to large language models, which operate on what's called a transformer architecture. But before that, let's look at very briefly architectures that were tried earlier but didn't work as well for text. So we had recurrent neural networks. The key issue with human text is that every word carries a link to the words that come before and the words that come after. And therefore, this context is important to propagate through the network as it learns. Recurrent neural networks tried to do this, but as the text got longer, as more words were fed into it, it started to lose a lot of the context from previously, called the vanishing gradient problem. So imagine by the time you are trying to train it on internet-sized data, recurrent neural networks will fail abysmally. For analyzing images, CNNs, convolutional neural networks, prove to be extremely effective. Convolutional neural networks slide a small filter across the entire bitmap of the image. And this proved so effective for images that people also tried to apply it to text, but it failed. Imagine a sentence like this: the cat that sat on the mat, which was near the window, was sleeping. What was sleeping? You and I know could only be the cat. Where was it sleeping? On the mat. Where was the mat? Near the window. Unless you bring in all of this context, the model is not going to learn the actual meaning of this sentence. And so to do that, came through a breakthrough paper in machine learning from the team at Google called Attention is All You Need. Before we get to this paper, it's important to understand that so far we've been looking at different mathematical models. A key aspect of all of these models is that they only work with numbers. Machine learning algorithms do not work with text. And therefore, we need one more critical component, which is convert words to numbers. And for this, we have a brilliant concept called word to vector. So far, we've been looking at different concepts in machine learning, but one key theme I have not highlighted, which is that all machine learning algorithms work with numbers. And therefore, we cannot feed text into neural networks. We need to convert text to numerical values. And to do this, we have a concept called word to vector. This is not a simple word to number conversion. It does so by understanding the meaning of the words and creating numerical values for words that are more closely related to each other. So imagine if you threw the entire English language into a multi-dimensional space. Then the word for king and queen, king, queen, crown, and royal would all appear in kind of the vicinity to each other. And this further preserves additional meaning. The famous king minus man plus woman is equal to, and predict the word queen. All of this happens because when the words are converted to vectors, the semantic value, the meaning of these words is captured, and the vectorization puts these words closer to each other based on their actual meaning. And now we come to this landmark paper from the researchers at Google, which came out in 2017. Attention is all you need. The breakthrough learning in this paper was that you don't need recurrence, you don't need convolution, all you need is attention. What does that mean? So the researchers said that we propose actually a simple new network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. And it said that this model performs brilliantly well on different parameters, specifically for language processing. The core problem, remember, is that long-range dependencies. How does word number 500 know that it is related to word number 1? The transformer's answer was, let every word look at every other word directly in parallel, but not with equal importance. The model learns to pay attention to focus on the relevant words for each position. Here's how it works. Each word gets transformed into 3 vectors: query, key, value. Think of it like a search engine. The query asks, where is the cat sitting? The key says, on the mat. We compare the query to all of the keys and get attention scores. A high score means high relevance. We use these scores to take a weighted sum of the value vectors. The result, each word's vector representation also captures the meaning of the other words that it attended to. And therefore, in the sentence, the cat that sat on the mat, which was near the window, was sleeping. Sleeping is for the cat, not for the mat. We don't do this just once. Multiple attention heads run in parallel, each learning to attend to different types of relationships: syntactic, semantic, positional. Stack all of these attention layers, feed forward networks between them, the neural network model we saw earlier, add normalization. The result is the transformer architecture. If all of this seems overwhelming, that's okay. This is a master's degree topic. It takes weeks and months for people to figure out intuitively what all of this means. And to admit to you, I'm not there either. One very interesting aspect that came through in this process was that you could take a sentence, mask certain parts of it, and train the model to predict what the masked value was. And based on this, you could then improve the parameters of the model. And so for this, you didn't need tons of labeled data. You just needed a lot of data. And so you could train these models on millions of tokens and scale it to billions and trillions of parameters. And scale, it turned out, was all you needed for emergent properties to come through. So what have we learned? A large language model is a massive mathematical construct that has billions of parameters that capture patterns learned from trillions of data bytes fed into it. And so what are the attack surfaces for large language models? The training data, poison that, and you modified the large language model forever. Weights, this is truly the intellectual property involved, modify that, and you again change the nature of the model. The embeddings, the word to vector conversions, poison that, and you also change the functioning of the model. Context windows, manipulate the context window and the model confuses. These are not just theoretical attacks. We're seeing models being poisoned. We're seeing models being jailbroken. And the reason all of that is happening is because these fundamental parts of the large language model can be manipulated. And this is what we shall deep dive into in the subsequent videos. Thank you for watching.